Yeah, I guess whatever we left off from last time, so starting from the middle of chapter 14, 15, and 16. Yeah, 2.5 chapters. Well, his question was the coverage about the final exam, Okay. Okay. So far, we've discussed we're starting from the hypothesis testing. That was a review, and then simple regression and multiple regression. So you have pretty much, of the basics of the regression analysis, including the structure and how to run the regression, how to test, and how to interpret, all those things, right? Chapter 15 is about the model building. Okay, so when you run multiple regression, I guess first question you encounter is, what variables you include as independent variable, okay? And, how many independent variable is good to build the best model to answer your question, right? Well, ultimate goal is, of course, you'd like to find the best model to predict your dependent variable, right? So, we talked about a few ideas like, dummy variable, okay, and interaction term already, right? But in chapter 15, we're going to go a little further and talk about a little more kind of refinement, how to refine our model in chapter 15. Okay? All right. The first topic is transformation of variables. Okay? And one thing that transformation does is, that allows us to handle nonlinear model, nonlinear relationship. If you remember, first assumption of the regression analysis was the linear relationship. We assumed linear relationship between y and x. Okay? In multiple regression, we assume the linear relationship with y and x1 and y and x2 and so on, right? So based on these assumptions, we could learn run the regression and make the interpretation and inference and run the test and whatever, right? But many times we can suspect, we have some cases where we suspect nonlinear relationship. Okay? I think last Tuesday I mentioned about the relationship between wage and experience. Okay? So if you look at the relationship between somebody's wage and labor market experience, okay, well, it's, I guess, natural to expect as experience increases, you can expect somebody's wage or earning to increase, right? But in reality, the relationship is not really linear, straight line, okay? Typical relationship is something like this, okay? The curvilinear relationship. Okay? So when you're young and fresh out of school and start gaining the experience, okay, your wage earning rises fast. Okay? But then it slows down, and eventually there will be a peak and even decrease after some years. Okay? So how do we handle this kind of nonlinear relationship, okay, when we need to include that information in our regression? Okay, okay, so that's the idea of the first thing that we're going to handle here. Okay? So it can be based on theory, logic, or scatter plot. Okay? Sometimes we can expect nonlinear relationship based on theory. Okay? In microeconomics, I think you've all learned about the average cost curve, AC or ATC, average total cost or average cost. Do you remember anything about the average cost curve? What's the typical shape of average cost? U-shape. That's right. Okay? So if you have dollar here and quantity here, right? As you increase your production quantity, typically we expect U-shaped ATC or AC or AVC, average variable cost. Those are things that are all U-shaped, right? So in case you want to find or try to estimate average cost curve, right? Find the equation for average cost curve, right? Then, of course, you will have to expect some nonlinear relationship. Logic, something like this, right? The wage and experience relationship, right? As the experience grows, we can expect the wages to rise, but eventually it can slow down, right? So, the slope is not going to be really constant all the way, okay? And then another way to find out is plot. If you suspect any nonlinear relationship, you can quickly create a plot, right? Just, create a scatter plot between the two variables, y and x1, right? And see how the plot looks like. Okay? Does it look like this straight line, or does it look like some curvilinear, right, relationship? Okay? So you can do any of these things, use any of these methods to figure out whether you should include any extra term in your regression. Okay? So first thing to handle this nonlinear relationship is including a quadratic term. Okay? You see here x1 plus beta to x1 square, right? This square term is called the quadratic term. And when you include this quadratic term, it's called the quadratic model. Okay? And I think you understand why including the second order term or square term can handle this curvilinear relationship, right? I'm sure you remember the shape of y is equal to a plus b x plus c x squared, right? Or let's make it simple. Y is x squared, right? And what's the shape of that curve? Does anybody remember? Which one? Okay. Something like this, right? Do I remember it correctly? Okay. And if it's negative x squared, and it's going to be like this, right? Okay. All right. Good. Yeah. So, that's why we think about this second order term or square term in order to handle curvilinear relationship. Okay. Okay. So how do we figure out the needs for this nonlinear fit, right? Well, here's another way of doing it that's called the residual analysis. We are quite familiar with the residual analysis already, right? Residual is error, right? So if the actual relationship between y and x looked like this, right? This sort of some sort of curve, right? Then if we fit a straight linear regression line, this red line, suppose we try to fit a straight linear relationship, straight linear regression line. So when you run the regression, you simply use y is beta plus beta naught plus beta 1 x1, right? You use this model to fit a regression line on this data, right? Then, as you see, in the beginning, you will mostly have negative error, right? The actual y will be below the regression line, so the error will be negative here in this area. But then the error will become positive in the middle of in the mid section of the regression line, And then after that, towards the end of the regression line, error will turn back to the negative, right? So if you plot the residuals against the x values, you're going to have this kind of pattern, okay? So if you see this pattern in your residual plot, then you can see, this relationship is nonlinear, okay? So by including the second order term, you brought some curvature in your regression model, okay? And then you can actually fit this nonlinear regression curve instead of line, I guess. This is a regression curve, right? Then, when you created a residual plot, your residual plot will look like this way, right? This is what we consider desirable pattern, right? Actually random, right? Instead of showing any pattern like this, right? We can consider this is a random distribution of errors. Okay, okay, so that's what we've been doing last time, right? So by looking at the residual plot, we can figure out whether there's any violation of assumption. Okay, okay. So as far as including the second order term or quadratic term, we can think about a few different cases. Okay? Once you run the regression, you can look at this coefficient of the x1 and coefficient of x squared, x1 squared, right? So by looking at these two coefficients, we can imagine or we can figure out the type of relationship, right? If beta 1 is negative and beta 2 is positive, what that means is as x1 increases, y value goes down, right? Because beta 1 is negative, right? So overall, we have this downward sloping relationship. As x1 increases, y value decreases, right? However, this beta 2 shows the slope of a slope. Slope of a slope, right? In other words, well, again, if you have this kind of relationship, right? Overall, there is a downward sloping relationship between y and x1, right? But that slope is not constant. Initially, the slope is very steep, but that slope becomes flatter and flatter, right? In other words, slope, the size of slope increases, right? This is this is something like -5, and then it becomes -1, right? And it becomes -0.5, something like that, right? So the size of the slope, magnitude of the slope increases, right? That's what this positive beta 2 implies. Okay? I'm pretty sure this is something you've learned in high school, right? Okay. If both beta 1 and beta 2 are positive, that indicates there is a overall positive correlation between y and x1, and the slope also increases. Initially, it is relatively flat, something like 0.5, right? And it becomes 1 and becomes maybe 5 or 6 or 7 or 1,000, right? So there is a positive correlation between x and y, and that relationship, the slope, increases. It becomes stronger. I mean, as the x1 increases by 1 unit, right? Initially, y value increases by 0.5 or 1 unit, right? But if you go to the larger value of x1, then y value increases very fast, right? That's what this positive coefficient implies, right? All right, so that's, you can figure out the rest of the slope and the shape of the curve, right? So once you run the regression, running the regression is pretty simple. If you suspect any nonlinear relationship, first thing you can try is including the square term or quadratic term, right? And you create, if you have y x1, you create x1 square by squaring all the variables, all the values of x1, right? So create another variable, right? And run the regression. That's all you need to do, okay? And then the next step is, of course, how to interpret and test the significance, okay? So you can test the overall relationship by running global test of model utility, right? You can do that, right? So null hypothesis says beta 1 and beta 2 are all 0, right? Alternative hypothesis says either beta 1 or beta 2. I guess you can say it this way, or you can, how do we say the alternative hypothesis typically in global test? And when you're running global test of model utility, what's the typical alternative hypothesis? At least one beta is not equal to 0. You can say that here too, right? So between beta 1 and beta 2, right? At least one beta is not equal to 0, right? That's, I think, easier way to do that. And test statistic is, of course, F statistic, right? And you can, you can run the global test of model utility. If you are interested in finding out just one variable, okay? In other words, whether this quadratic term makes any difference, right? Do we really need to include the quadratic term in our model, right? Then you can simply run a test on this beta 2, right? So null hypothesis says beta 2 is not equal to 0. Beta 2 is equal to 0, right? What that means is this square term does not make much difference in the value of y, right? Alternative hypothesis claims quadratic term is significant or it improves the model, right? So you can run that test. That's nothing new here, right? I'm sure you all understand that. Testing the quadratic effect, another way to test the quadratic effect is comparing the R square from the simple regression to the adjusted R square to from the quadratic model, right? You remember the concept of adjusted R square? Adjusted R square adjusts the R square based on the number of independent variable, right? Because the nature of regression analysis, multiple regression, is as you increase the number of independent variable, R square always increases, right? And sometimes, even if you include some independent variables that are completely nonsense, okay? They're completely non-related, right, to actual dependent variable, right? Mechanically, mathematically, R square will increase by just having more and more independent variables, right? So adjusted R square is designed to compensate this problem, right? Compensate the size of R square considering the number of independent variable, right? To avoid the overfitting problem, overfitting temptation, right? Okay, so let's see. All right. So if adjusted R square from the quadratic model is larger than the R square from the simple model, then the quadratic model is likely a better model, right? Why is that? Because you have beta naught plus beta 1 x, and y is beta naught plus beta 1 x1 plus beta 2 x1 square, right? Typically, when you calculate the adjusted R square, right? Adjusted R square is smaller than regular R square, right? If you look at any, computer printout, what was it last time? Yeah. If you look at R square here, it's 0.796. Adjusted R square is 0.759, right? So typically, adjusted R square is smaller than the regular R square, right? But when you calculated these ran two regressions, look at the R square here and look at the adjusted R square from here, right? And if adjusted R square from this model happens to be greater than the R square from the simple regression, or the regression without the square term, right? Then you can pretty much say that the adjusted, that R square term, this square term of x1 makes some significant contribution. You all remember the concept of R square, right? R square is SSR over SST, right? Explained variation divided by total variation, right? So R squared tells us just how much of the total variation in the dependent variable is explained by independent variables, okay? So, when you included x1 and x1 squared, right, you can calculate the adjusted R squared. And if this is greater than the simple model R squared, right, then you can say this is making significant contribution, right? Even after being penalized for having one more independent variable, right? If the adjusted R square is still greater than R square, right? That's an indication that the square term is making a good, significant contribution, okay? Okay. And then here's an example. What's going on here? Okay. So here's a textbook example of the including the quadratic term. So suppose we have some filter, either air filter or water filter, right? And we're trying to find out the relationship between the number of times you filter water or air, let's say water, right? And then you measure the purity of the water, right? And what kind of relationship is there between the number of times you filter and the degree of purity, right? And let's say when you look at the scattergram, it's always a good idea to look at the scattergram before you run the regression, right? And you see this kind of relationship, right? So the question is this a linear or nonlinear relationship, right? So it's hard to tell by just looking at it, right? Is it better to fit a straight linear regression or nonlinear curvilinear regression, right? Well, in that case, you can try both, right? So in the first time, you run the regression with only the regular number of times filtered, okay, as an independent variable, just one independent variable, right? That's a straight linear relationship, right? And then you got this relationship, and when you look at the residual plot, you got a problem there, right? When you look at the residual plot, you see this clear pattern, right? Initially, you get positive error, and then it becomes negative, and it becomes positive, right? So that's a clear indication that this is actually curvilinear relationship. And because you fit a straight line here, right? Initially you have positive error, negative error, and then positive error again. Okay? So second time you include the square term, okay? Time and time squared, okay? And run the regression, okay? And look at the residual plot. Residual plot looks like pretty random. You don't see any pattern, clear pattern there, right? So residual plot against the time and against the time squared, right? Both look pretty good, right? Pretty random, no clear pattern. And then another thing you look at is adjusted R-square. Adjusted R-square from the second order model is 0.994 as opposed to 0.968 in this straight line model, right? So explanatory power is clearly larger with the second order term, right? Compared to the simple straight linear relationship, straight linear regression, okay? Okay, so this is a pretty hypothetical example, right? And in this case, it's clear indication it has that the second order term is significant. You should fit quadratic model rather than straight linear model, okay? Any question so far about the quadratic model? Okay, good. Actually, this is just one introduction to transformation, right? And this is actually the most typical, most frequently used transformation, right? If you look at any research, right? Many times you will see the second order term, right? Or quadratic term in the model, like experience square. But actually there can be all kinds of transformation, right? What about, for some reason, you suspect relationship goes like this. Does it remind you of any curve that you learned in economics? Yeah, but in economics, have you seen any kind of curve looking like this? Huh? Productivity? Productivity. How about total cost curve? Total cost curve, right? That's a typical shape of total cost curve, right? Total cost and the output, right? So initially it slows down, but there is some inflection point. Then after some quantity, right? It accelerates, total cost accelerates, okay? So if you have total revenue is P times Q, right? Okay. So if you're selling your output, say at $5, if the price is $5 per unit, right? And if you sell 100 units, right? Then your total revenue is $500, right? So total revenue is a straight line, right? The slope is 5 in this example. Anytime you sell one additional unit, right? Your total revenue increases by $5, right? So the profit is total revenue minus total cost, right? So what that means is initially your total cost exceeds total revenue, right? meaning your profit will be negative when you start your business and just starting out the production, right? Typically, your profit will be negative, right? But then after a certain point, your profit will be positive because total revenue is greater than total cost, right? But then if you produce too much, then your cost accelerates, right? And your profit will be negative again, right? So if you look at the profit output relationship, there's going to be something like that, right? There will be profit maximizing quantity, right? And profit maximizing quantity actually happens here, right? So we're talking about the maximum distance between the total revenue and total cost, okay? And usually in intermediate microeconomics we teach this, but I'm sure in Korea, in principles of economics, they also teach this too, right? So, well, actually in principles economics, we just give you marginal revenue equals marginal cost as the profit maximizing condition, right? But what that means, the marginal revenue is the slope of the total revenue curve, right? Marginal cost is the slope of the total cost curve, right? So what that means is if this is the profit maximizing quantity, at that point, this slope of the total cost curve is equal to or parallel to the slope of the marginal revenue curve, total revenue curves, something like that, right? Anyway, so if you suspect this kind of relationship, right, then we have what? We have one more, the change of direction, right? Initially, we go this way, and then this way, right? So we can, you remember y is x cubed. Typical shape of y is x cubed, y equals x cubed, right? You remember? Yeah, kind of S shape, right? So if you have this kind of relationship, it's going to look like this, right? Am I right? It's been long since I've learned this. Yeah, right? Okay, so yeah, this, if you suspect that kind of relationship, then you can try one more term here, right? So beta naught plus beta 1 x1 plus beta 2 x1 squared plus beta 3 x1 cube, right? To handle that kind of relationship, right? And see what happens with the regression, right? Does it improve the fit, right? And that's another way, another example of transformation, right? Transforming the independent variable, right? Here in our textbook, they talk about the square root transformation. Okay? Square root transformation is typically used to overcome violations of the constant variance assumption. Constant variance assumption. What's another name for this? Constant variance or equal variance assumption? We have a weird term for this, right? Constant variance. You remember that term? Equal variance? Huh? What's that? I'm talking about the terminology. Homoscedasticity, right? Homoscedasticity, right? Yeah. That's the equal variance assumption, right? If you have problem, in other words, if you have unequal variance, it's called the heteroscedasticity problem, right? Heteroscedasticity, right? All right. So if you have some heteroscedasticity problem, violation of homoscedasticity assumption, right? then many times you can use square root transformation, right? Well, square root, if you remember, y is equal to square root of x. Does anybody remember the shape of this curve? How does it look? Yeah, that's right. Goes like that, right? If you have x and y. Yeah, you can, if you have y, x, I'm sorry, x, y, right? If x goes 1, 2, 3, 4, 5, 6, right? And y goes for what? 1.414. What's the square root of 3? I don't remember. 1.7 something, 2 point something, right? Yeah. So you can easily create that, yeah. 1, 2, 1.4, 3, 1.7, right? Something like that. Right? Okay, right. So we have the original relationship like that. Okay? So if you have the y is square root of x, then we have this kind of relationship, right? Then what we can do is think about the square root. Think about the relationship between square root of x and y. Okay? And so, oops, shouldn't have. Okay. To make it simple, then I'll go L1, 4, 9, 16, 25, right? Then y will be 1, 2, 3, 4, 5. Okay? All right? Then, if you transform x to square root of x, what's going to be the relationship? It's going to be 1, 2, 3, 4, 5, right? And y will be 1, 2, 3, 4, 5. Right? Make sure you understand what I'm doing here, right? We have original relationship is y is equal to square root of x, right? Then we'll have this kind of relationship, right? So if you transform, right, the variable, right, then the relationship between this independent variable and y, dependent variable, will be straight line, right? So you're converting this kind of curve to straight linear relationship, straight line relationship. Okay? All right. So, what if you do this? Then what happens is the original, residual plot, it looked this way, right? When you take a square root, right, it can straighten this way, right? Because we are kind of concentrating, right, the size of the variable, right? We are artificially concentrating the variability of x variable, right? So when you have this is a typical the symptom of the heteroscedasticity problem. If you have this kind of residual plot, right? Then when you convert the relationship, right? Convert the x variable, you can have this kind of residual pattern, right? So that means you can run the regression now, right? That's the you are artificially conforming the relationship or the residual plot to be normal. I mean, satisfying the assumption, right? Okay. Okay. So that's the idea of square root transformation. Okay? Another very popular transformation is log transformation. Okay? Okay, this requires a little bit of discussion. Right? Is everybody okay? Okay, all right. So make sure you pay attention here. Right? Log transformation is a very, actually log transformation is a lot more popular, a lot more frequently observed, right, than the square root transformation. Okay. So far, we've been talking about model like this. Y is beta naught plus beta 1 x1 plus beta 2 x2 and so on. Right? And this is what we call additive model, because all the independent variables are added to each other. x1, x2, x3 are added, right? There's another type of model. It's called the multiplicative model. Okay? And that goes like, which is the easiest way? Yeah, okay. Yeah, this is the simplest type of model. Okay? So instead of adding the intercept to the next term, they are multiplied. Beta naught times x1 to the power of beta 1. Okay? And actually, the error term is multiplied, right? Okay? Instead of, since we are talking about the model and population parameters, we have to include the error term. Okay? Once you estimate, the error term disappears. Okay? So what kind of model are we talking about? How many of you have learned the Cobb-Douglas production function? Cobb-Douglas. Nobody? Okay. Well, either intermediate micro and intermediate macro courses will introduce the Cobb-Douglas production function. Okay. And this is most popular format or form of the production function. Production, what is a production function? Production function defines the relationship between output and inputs. Okay? So if you think about it, whatever you produce, you will need many different inputs, right? Even in a very simple product, right? You're typing. I guess these days this job is really rare, right? But there used to be the job called the typist, right? And there was a typing business. I mean, when I started at graduate school, right, there was no personal computer. Can you imagine? There was no such thing as word processing software, right? So everything had to type, right? And when I actually, before I went to the United States, I worked in Korea for about 7 months, okay, as an insurance adjuster, claims adjuster. Okay? So in Korea there are chaebol groups, right? Chaebol groups, right? And the company I worked for belonged to Korea Explosives. Do you know what that is? Yeah, 한국화약, right? It used to be 한국화약 Group, Korean Explosives Group, right? Now they call it Hanwha Group, right? So they hire as a group. When they hire new employees, right? Usually new college graduates, they hire as a group, right? And I don't know these days, but in the old days, once you are hired, selected, okay, they had about 10 days, 2 weeks training, right? So they put you in some kind of training camp, okay? And go through all kinds of, physical and all kinds of game and whatever, right? The group environment, okay? And they observe your behavior, right? How you handle the stress or personal relationship or whatever, right? And after the training, they assign you to different company because these groups have 10, 20, 30, 50 different companies. Right? So when you apply for this group, you have no idea what kind of job you're going to applying for. Right? So after about 10 days or 2 weeks training, I was assigned to an insurance company, and I had no idea what I was going to do. Right? I just got the notice that come to this building, 10th floor, by some 9 o'clock Monday. So I arrived to this building in front of City Hall, right? And I went to 10th floor, and so reported to my first job, first day of work. Right? That was amazing. It was a huge room, about 30 workers in this space, right? And at that time, again, there was no personal computer, right? And this was an insurance company, right? So everything had to be typed. You guys know typewriter? Have you seen typewriter? Right? And at that time, the most popular typewriter was called the IBM Selectric typewriter. It's a huge, it's about 20 kilogram weight. And if you press a key, there is a ball, and this ball has all the letters on the surface. So if you press A, and it quickly turns and make an impression on the paper through the tape, right? So you see the A on the paper, right? The electric typewriter, right? But the thing is, this thing is extremely noisy, right? So when this typist, out of 30 people in that space, I would say at least 15 were high school graduate women employees. And their job was just typing. All day, every day, they type, right? The insurance policies and all kinds of documentation, right? And they are really good in typing, right? They're really fast, right? And when they type all these documents, it sounds like machine gun. Right? And imagine you have this about 15 typewriters, going at this rate, right? And it's extremely noisy, right? And then at that time, everybody has a telephone on their desk, and the ringer of telephone was a very old sound, old ringing sound, not like this, music sound like today, right? Bell sound, right? So telephone rings, and since it's so noisy, everybody yells, "What?" So another thing is at that time, I would say about 90% of Korean males smoked everywhere, right? Inside the office, in the classroom, professors smoked, right? Can you imagine? And when I was in college, professors smoked while teaching and just dropped it in. Okay? So this room was filled with the smoke and the noise. Everybody was yelling, right? It was like a battlefield. Right? How was I talking? I forgot, right? Anyway, I survived there for about 7 months. And it was quite interesting. I learned a lot about the life and insurance and actually work environment in Korea, right? The production function. I was talking about production function, right? So even if you run the very simple, there's another thing I have to mention. So I went to the United States graduate school, and the last process of the graduate school is dissertation, right? So you take all these courses for master or PhD degree, right? And then there is a comprehensive exam, right? Usually it takes 2 days. For 2 days you take exam. So first day you take in the morning microeconomics, and in the second day at the afternoon you take macroeconomics, right? And then the second day you take exam on your major field, labor economics or whatever, right? So when you pass this exam, then you need to write dissertation, okay? And I got a job as soon as I started the dissertation, so it took me about 2 years to finish this dissertation, right? The thing is, fortunately, when I was starting dissertation, IBM came up with the PCs, personal computers, and the Microsoft Word, right, came around. So it was very convenient, right? But a few years before me, everything had to be typed, right? The typical dissertation is about 150, maybe 200 pages long, right? And you type all this dissertation and bring it to your advisor, right? And advisor makes the mark and, delete this paragraph, right? If you delete one paragraph in page 10, what happens? You have to retype the whole thing again, the rest of 190 pages, right? You have to retype, right? So there was a typist job, right? Usually the secretaries in the universities, they had this side job, right? And I think they charged about $1 per page or something like 50 cents per page, right? So even in this simple business, you will need paper, typewriter, and then of course labor, right? Labor is the most important input, right? So that's the idea of the production function, right? And the Cobb-Douglas production function is the most typical, the most frequently used, the format, right? Form of the production function that we use in economics. Okay, I'm going to continue this on Thursday. All right. Any question today?